All right, our next example here is um, solving. All right, so now we're technically going to start calling these systems of equations, right? Two equations with two or more variables where we're looking for the value of x and y that satisfies both of these equations simultaneously, right? So this was an Algebra 1 keystone concept that you guys have mastered over and over again. So we're going to talk about the elimination method. I'm going to use a unique scenario here, again, because most of you have mastered the elimination method over and over again. But there's some unique scenarios where you have to pay attention to. So when we're using the elimination method, our goal is to kind of look at the two equations and analyze them, figure out which variable is going to be the easiest variable to eliminate. Meaning I'm going to have to multiply one or both of these equations by a value, a constant, so I can produce opposite coefficients of either the x's or the y's. So looking at this, I usually just target the first variable. I see x here, and I can see that I can easily manipulate this bottom equation, 3x plus 2y equals 4, by multiplying it by -2. And that'll give me a -6x here, which will allow me to eliminate with the top equation. Now, I'm also going to tell you we're very used to multiplying to produce opposite coefficients in this case. But remember, you can also multiply by a fraction, which is the same as dividing, right? So instead of multiplying the bottom equation by -2, I could actually divide the top equation by -2, and that'll give me a -3x here. Or instead of dividing by -2, that's the same as multiplying by -1/2 here. So let's start with that process, right? So we're going to multiply the left equation here by -2, and that's going to produce -6x minus 4y equals -8. And then I'm going to bring this top equation down. And then when we use this elimination method, remember the best case scenario is to add them. The x variables eliminate, but coincidentally, so do the y variables and the constants. So in this is a unique scenario because both pairs of our variables have eliminated. And now we're left with this equation, 0 equals 0. This is a true statement, right? So in this type of scenario, when both pairs of variables eliminate, you're either going to be left with a true statement or a false statement. For example, if it was 0 equals 1, that's false. If it's 0 equals 0, that's true. So if it's a true statement in this case, then we have to understand that both of these equations, 6x plus 4 equals 8, 3x plus 2y equals 4, these are both the exact same line on the graph. They're different equations in appearance, but they're equivalent. So they're actually the same line. And the answer, if we were to solve this system, would be infinite solutions in this particular case. If the variables eliminated each other and this was not a true statement, then they are not the same line. In fact, they're parallel lines, and that answer would be no solutions, right? So this would be the unique case, right? And then we have this scenario, right? So we have 3x minus y equals 9. 7x minus 5y equals 25. So the idea, the method here is to use the substitution method. And to start, again, you know this, but you want to analyze the equation and look for the easiest variable to solve for, meaning what's the least amount of work to solve for a variable. And you want to keep in mind, is that also going to reduce the possibility of dealing with fractions, right? For example, if I solve this equation here for y, I'm going to be left with a fraction of 7/5 on the other side of the equation. And I'm going to be left with another just 7/5. If I solve this equation for x, I would be left with a fraction of, 5/7 and 25/7, right? Fractions cause problems, so if we can avoid them, we should. So isolating y in the top equation appears to be the best case scenario. So what we're going to do is we're going to subtract 3x, divide by -1, and we're left with y equals 3x minus 9. Now here comes the substitution part. We're going to substitute the expression for y, which is 3x minus 9, into the y variable in the other equation. It's very important it goes into the other equation. And then we're going to solve that equation for x, because now we have an equation in terms of x only. So we can solve this equation for x. Careful when you substitute 3x minus 9 into this y variable, make sure it's grouped, because in most cases you're going to be distributing some value, whether it's positive or negative there. So I distribute, I continue to solve, and I end up with x equals 5 halves. Not done, that's just the x value, right? And now what we got to do is we have to take this value and we're going to substitute one more time. We're going to substitute 5 halves into either of the original two, right? Doesn't matter which one you go in for this second substitution. I'm going to choose to go into the top equation because it just looks easier to work with for me. So I'm going to substitute 5 halves in. I have 3 times 5 halves minus y equals 9. That gives me 15 halves. And now I'm going to solve for y. So I'm going to subtract 15 halves, divide by -1, and now I have y equals -3 halves. Now I've solved this system. I have a point of intersection. That point is going to be the coordinate point, 5 halves comma -3 halves. Again, must be expressed in an ordered pair as a coordinate point here.